Hello class, welcome to the lecture on taint analysis. This is the first lecture post the midterm exam. So today's lecture is going to present the concept and applications of taint analysis, which is a very important method in computer security, in computer system security. Taint analysis is a method that has a long history going back to the late 70s, almost to the beginning of the field of computer security when the principles of the field were laid out. However, it saw a resurgence in around the mid 2000s when fresh applications of this technique were found for things like detecting memory errors, for example, buffer overflow exploits or format string exploits. And we will see that taint analysis has a number of other applications, and we will revisit taint analysis multiple times throughout the course. So we are going to be looking at some applications, for example, of taint analysis in web security, in mobile application security, and so on. But we will start with an application of taint analysis to the concept of to detecting memory errors. So there is a vast history of methods and a vast body of literature uh, that covers the methods of taint analysis and applications of taint analysis. But the paper that I have chosen for you is one of the early papers of taint analysis that shows how taint analysis can be applied for memory error detection. And as you can see, that is the paper, this dynamic taint analysis for automatic detection, analysis, and signature generation of exploits on commodity software. This is a paper from 2005 from the NDSS conference. And in today's lecture, we won't go over this paper line by line or essentially the way that they describe it. Instead, I will tell you about the concepts of taint analysis more generically, because some of the concepts have evolved, matured, and have been applied differently than this paper originally introduced. Now, having introduced that, I will also make the connections with this paper where I see the connection as being appropriate so that you can connect up the concepts that I'm discussing in class with the concepts as discussed in this paper. Okay, so with that said, let us get started. So, okay, here. So here's the basic outline of how today's lecture is going to proceed. These slides are not mine. These are borrowed from a source on the internet. So the way that we are going to organize this lecture is that I'm going to talk about the basic concepts of taint analysis first, then describe how you can implement taint analysis on the x86 architecture, the Intel x86 architecture, and then talk about various tainting rules and some advanced methods. Okay, so what is tainting, right? Or what is taint analysis? So a taint analysis is a method by which you can try to measure the level of influence that some external data that your program consumes has over the execution of the application. Okay, so for example, your application might read network packets via socket, or it might read things like PDF files if it is a PDF file renderer, for example, or it might read things from the command line. Now, all of these things, for example, the network packets, the PDF files, the command line inputs, and so on, are the inputs to the program. And the program behaves in different ways for different inputs, right? It takes different paths, follows different paths for the different inputs that are fed to the program. Now, the goal of taint analysis is to identify which program variables are triggered, which statements are triggered, which memory locations are impacted by a particular input. Okay, so that is the basic motivation for taint analysis. You want to track the flow of the program's execution through various program artifacts like statements, like variables, like memory, and so on. Okay, so let's begin with the description of the concepts. So you can, in fact, so taint analysis goes by another name, and this is the classical name for taint analysis. It's also called information flow tracking. Um, we will look at information flow tracking or information flow control in slightly more detail later in this course, but this is your first introduction to it. Okay, so and the motivation for information flow is very clear, right? If you try to, let's say, take an application, put it inside a debugger, and you were to, let's say, do a single step execution of this program, you will find that data is being copied all the time, right? Data is being copied from memory into register, from one register to the other. As you do computations on, let's say, registers on memory, for example, you add or you subtract, various flag registers are set, and then when you copy the data back from the registers into memory, there is information flow from the registers into memory. Okay, so information is always moving in memory as well as the processor registers, and this happens during the course of the computation. And so taint analysis is a form of information flow analysis where you're trying to reason about the flows of various pieces of data through the program's memory as the program executes. So there is a historical definition of information flow control, um, and to determine whether a program is secure from the perspective of information flow control. And this goes back to one of the founders of the field, Dorothy Denning. And so she defined certification of programs for secure information flow in the following way, right? So a piece of information flows from an object X into an object Y, denoted by X arrow Y, whenever there is information that is stored that's in X is transferred to object Y. And this can happen in many ways. So for example, if you have a statement in your program, Y equal to X, and X and Y are, let's say, both integer variables, that very statement Y equal to X is a statement that transfers information, that it causes information to flow from one location to the other. Okay, and you will see as I talk further, as I explain these concepts further, this is called explicit information flow, because you can actually see the flow of information going from the variable Y, from the variable X to the variable Y. Now, if you had another statement, for example, Z equal to X plus Y, that is also an example of information flow, because information flows from X to Z as well as from Y to Z. Okay, information flows from both the operators to the variable that stores the result of the operations. So we want to reason about security. We want to reason about information about the behavior of the program in terms of these information flows. So here is a pictorial depiction of a flow. So a flow is nothing but an operation or a series of operations that uses the value of some object, for example, X, to derive the value for another object, for example, Y, and this causes a flow from X to Y. And you can see on this slide over here. So there's an object X, it stores some information. Maybe it's a variable that stores, let's say, the value 5. You're doing some operation on it. Maybe you're taking the negative, you're taking the sign, or maybe the operation is a binary operator that takes two variables. Okay. But whatever it is, the result of the operation is stored in the object Y. And so the object Y is getting some information that is derived from the object X. Okay, so we say in this particular case that there is information flow from X to Y via this particular operation. In fact, there could be multiple operations, in which case the information flow is through that series of operations. So the term taint analysis stems from the fact that we in the security community like to refer to tainted objects. So what's a tainted object? A tainted object is one uh, whose value is affected by an untrustworthy source. So as you saw from the previous slide, there are flows of information from one object to the other. Okay. Now we might depict certain, or we might denote certain of these objects as trustworthy objects and the other objects as untrustworthy objects. So for example, if you're a network facing program, then any variable that reads packets from a network facing socket, that variable that represents the socket is going to be an untrustworthy object, because the attacker can send arbitrary input that he or she controls to that object. Okay, so that is going to be called an untrustworthy source, shown in this blue box in this picture. And if through one operation or a series of operations, the object X gets its value, or its value is influenced by this untrustworthy source, we say that that particular object X is tainted. Okay, so to determine whether an object is tainted or not, we generally associate a taint, a label or a tag with the object, and this is called the taint label or the taint tag. So when an object, for example, as shown in the previous slide, uh, gets tainted by copying data from an untrustworthy source, the object will be marked tainted. It is generally the taint label or the taint tag is generally a bit that is associated with the object in some way, that in this particular case tells you whether the object is tainted or not. In general, the notion of labels and the notion of tags is much richer, and you can use it to propagate various kinds of properties about the object as well. So for example, you can propagate information about the object's data lifetime, or you can propagate information about which source it came from. All of these things are possible. For this particular lecture, we'll only be concerned with a very simple taint tag, where the taint tag, you can think about it as one bit or a boolean that tells you whether the object has been tainted or not. So the tag allows you to track the influence of the tainted object along the execution of the program. So whenever we start talking about tainting, there are two important concepts that one has to keep in mind. There are three concepts rather. So the first concept is that of taint sources. The second concept is that of taint propagation. The third concept is that of taint sinks. Okay, so sources are the place from which taint originates. So sources are the locations from which you start reading untrusted data. Propagation describes how taint tags flow through the program's objects as the program executes, and taint sinks are essentially places where you want to check whether tainted data is being used in some way or not. And we will look at each one of these concepts in more detail. But before I proceed, I would like to draw an analogy to the concepts that are described in the paper, as described in the paper. So if you look at the paper, the terms that they use are slightly different. So taint sources are also called taint seeds. Okay. Taint tracker is the propagation of the taint, and taint assert is where you check at the sinks whether the object that is being used is tainted or not. Okay, so this particular picture over here that's how to interpret the various terms over here: taint seed, taint tracker, as well as taint assert. All right, let's go back to the slides. Um, oops, just a moment. All right, I'm sorry about that. So taint sources include things like files that you read from disk. So these are untrusted files, for example, MP3 files, PDF files, and so on, that you may actually download from untrusted sources. So the attacker has the ability to control the contents of these files, and therefore these are places from which you read untrusted data into your program. Your program consumes untrusted data in the form of MP3s, PDF, and so on. In fact, it is a fact that the most vulnerable programs, the programs that are most vulnerable to memory errors are ones that actually parse things. For example, flash players, PDF readers, because they have to support various formats and because they are actually reading stuff from large files. These programs tend to do manual memory management, and there are lots of errors in the manual memory management, especially in the part where data is ingested. Okay, so these kinds of programs are especially known to be vulnerable to memory error attacks. The parsers of these kinds of files, I mean, and so the files themselves, that is the PDF files or the Flash files and so on, are the taint sources. Likewise, things like data received from the network is also untrusted. Data that comes from the keyboard, which is, command line input, mouse, touchpad input, and so on, are all taint sources. So what is a taint source and what is not a taint source depends upon what is the so-called attack surface of your program. So the attack surface of your program is the set of interfaces of your program that is exposed to the attacker. So the program is executing in a certain way, and you want to protect the execution of the program. Whatever untrusted input the program interacts with, that is a taint source. So it very much depends upon the particular scenario in which your program is being used, and whatever is untrusted, whatever the attacker can control in that particular setting, in that scenario, is supposed to be a taint source. So the task of taint propagation is to take data that's coming from untrusted taint sources. So taint sources are by definition untrusted and therefore tainted. And then the job of taint propagation is to identify how these objects that are derived from untrusted sources work their way through the program. So if an operation uses the value of a tainted object uh, and derives another object, that second object, the derived object, also becomes tainted. Okay, so we say that the object X tainted the object Y. Okay, so the taint operator in this case is that if X is tainted, then Y is also tainted, and this taint operator is transitive. Okay, so if X taints Y and Y taints Z, then we say that X has indirectly tainted Z. Okay, so that's what we mean by this taint operator, which is essentially telling you why or what was the source of this taint. Okay, so here is another way, a pictorial way of representing taint and how it propagates through the program. So you can imagine this graph is, let's say, some kind of control flow graph in your program, or data flow paths that are there in your program. And as you can imagine, maybe k is a variable that is being computed in some location of the program, and maybe the value of k is actually being influenced by an untrusted source, right? So k could be, for example, a variable that you end up reading from the command line. So because the command line is untrusted, according to our taint sources, k becomes untrusted. Now k might be used to compute the value of L and M, so those also become untrusted, as well as Z. Okay. Similarly, maybe X is, you read an MP3 file and you stored the contents of that MP3 file in some buffer, and so maybe this X over here is the is the buffer that is storing this untrusted MP3 input. Okay, so uh, so now what happens is that this untrusted buffer is, so that's untrusted source is working its way to X as well as W, but maybe you are applying some filters to the MP3 image to modify it. So that buffer gets copied over to Z, then maybe you're also applying some command line parameters. So Z maybe is like a transformed video buffer that contains inputs from both X as well as K, but because X is untrusted and K is untrusted, Z is also untrusted. And it is a merger of um, information from two different untrusted or tainted sources. Okay, so we will look in much more detail about how things get tainted, rules for tainting, and so on. All right. So one of the applications of taint analysis is exploit detection. Okay. So the idea is that if you can track user data in the program or untrusted data in the program, you can detect if untrusted data reaches a privileged location. Okay. So in particular, so imagine that you had a way to do taint analysis where you were to tag every memory location in your program with a bit that determines whether that memory location is storing tainted information or not. Okay. So now if your program is, let's say, reading untrusted data from the command line or from a network input, all of those memory locations that directly get their values from the command line or from the network input would have would have a taint bit set. Okay. So they are storing taint information. So as the program executes, of course, more and more stuff gets tainted as the way that I just showed you, taint propagation happens. And so how do you detect whether something is an exploit? Well, let's look at stack-based buffer overflows. What happened in a stack-based buffer overflow? So in a stack-based buffer overflow, the attacker was able to overwrite the return address. Okay. So supposing we were to consider the memory location that stored the return address as a taint sink, and we were to check the policy that taint sinks must never be tainted, then if you have a buffer overflow attack that overwrites your return address, essentially what happens is that the return address memory location also will be tainted, and the reason is because you're copying untrusted user untrusted attacker provided input into the memory location stored by the that stores the return address, as a result of which that particular memory location gets tainted, and as a result of which, if you were to check whether taint sinks are not supposed to be tainted, you will immediately flag an error. Okay. So that is how you detect things like buffer overflow attacks using um, taint analysis. We will look in more detail. I will explain to you how are done on the x86 architecture. But this basic technique has many, many, many other applications. So for example, you can use the same taint analysis technique to detect SQL injection, which is a form of database attack that is very common in the web, in the domain of web applications. It can be used to detect what are called XSS or cross-site scripting attacks. We will also study these attacks in much more detail once we start the topic of web security. Okay, so this technique of taint analysis is very versatile. That's what I'm trying to emphasize over here, and you will see its incarnation in many ways, and very often it's a solution that comes very handy. So Perl, uh, actually nowadays I don't know how many of you are familiar with this language. Perl is the precursor to Python in some ways, and Perl actually had a tainted mode that allowed you to, track the flow of data through the execution of the Perl program by its interpreter. So the major advantage of taint analysis is that it allows you to detect even unknown attacks, right? So you don't have to have any sort of template for the attack. You just have to set up the policy that taint sinks must not use information that is untrusted or tainted, and if you were to just check for this policy, you can detect all sorts of attacks where trusted where locations such as the return address end up getting untrusted or attacker provided data. Okay, so and that's what is called taint assert in the paper. So before the execution of any statement, you just have to check this taint analysis module, or the checker checks whether the statement is tainted or not. And if it is tainted, you issue an attack alert. So that's the basic idea behind the technique of taint analysis. And now what we will do is that we will study how taint analysis can actually be implemented on the x86 Intel architecture. You can implement taint analysis at the level of machine instructions. Um, of course, taint analysis, if you were to propagate additional information in software, it's going to add an overhead. People have also explored how to do it in hardware itself. So let us now look at how to implement taint analysis on the x86 architecture. So there are quite a few taint analysis tools for C, C++, and Java. These all work by actually instrumenting the program. So, you can imagine a source to source transformation that, for example, takes a C program and creates a new C program where you have added additional statements that propagate taint information. But we will look at x86, right? I mean, if you can do it in x86, it is general enough, and we can apply it to assembly code. So the main advantage is that you can now think about the taint analysis completely at the machine code level. Even if you don't have access to source code, you can perform this taint analysis and detect these attacks. Okay, so it allows you to avoid having to create high level parsers for each programming languages and so on. You just directly rewrite the binary by applying instrumentation, and you're able to do taint analysis. So this should remind you very much of the approach that was used, for example, in the CFI paper. So the CFI paper also used instrumentation. The important point with the CFI paper was that you did not have to trust the instrumenter. You only had to trust the CFI verifier, which was much smaller than the CFI instrumenter. But here we are not going to actually have such assumptions. This is going to require some heavy lifting in terms of trying to understand how taint is applied. Okay, so let's proceed. So with respect to x86 instructions, the taint analysis module that essentially checks whether or decides how to propagate taint and checks whether data is flowing to the sinks. It must identify the operands of each instruction. That is, uh, every instruction has certain operands that it uses in order to perform its computation. It must be able to identify the operands, and it must be able to identify the source and the destination, right? Because, for example, if you have a move instruction that has two operands, you should be able to identify which is the source and which is the destination. The reason is because the taint actually flows from the source to the destination. Okay, and this is how you track the taint of objects, the how the taint flows. So what this requires you is to understand the semantics of each instruction, which is the meaning of each instruction, how each instruction works, and so on, so that you can develop taint flow rules for every x86 instruction. So once you develop taint flow rules for every individual instruction, saying, look, taint, if the first argument is tainted, then after the execution of this instruction, the second argument also gets tainted. And if you can do this, for instance, for every instruction, you can develop such rules or the semantics for each instruction. Now you just have to apply these rules one by one for during the execution of the program, and you can implement your taint analysis that way. Okay, so typical instruction, for example, in this particular case, you have move EAX 40 hex. It has two explicit operands. In this case, EAX is one of the operands, and you have a literal value. It's not a variable. It's 40 hex, and the destination in this case is EAX, and the source is this immediate value. So this is an easy case where you have explicit operands. The operands are actually mentioned in the instruction itself, and that's a great thing because now you don't have to worry about whether there are any side effects of this instruction. But some instructions also have these implicit operands, the other things that are affected when the instruction executes that you don't visually see when you look at the instruction. Okay, so here is one, right? I mean, like you've got push EAX. The explicit operand, of course, is that EAX is one of the explicit operands, but then it also has an implicit semantics where when you push something on the stack, the value of ESP is going to reduce, right? The value of uh, of the whatever is stored in EX gets stored onto the current top of the stack, right? So there's a subtraction operation and there's a move operation, and in fact, if you're talking about the x86 32-bit architecture, it used to use the notion of segments. So there is a corresponding segment register which is shown as SS, right? So the segment register colon ESP is now EX. If you're thinking about the x86 64-bit architecture, it doesn't have the explicit notion of segments. So that would not really be something that you have to concern yourself with. So in this particular case with push EAX, there are some implicit operands, which are the ESP register, which is clearly affected, as well as the segment register. Okay. So then the question becomes, how do we deal with these implicit operands that are not visibly part of the instruction or complex instructions? Okay. So there are many ways to do so, but nowadays, so one painful way to do so is to go and look at all of the x86 instructions. There are more than 1,000 of them, right? I mean, if you were to look at the x86 instruction set architecture and painfully list down, what are the operands? Somebody has got to do it, but if every person writing a taint analysis says to do it, it's going to be a very error-prone process. So what has happened is that people have there are some groups that have actually done this painful heavy lifting and have come up with intermediate languages that take the x86 instruction set and translate them into an intermediate language that actually encodes the effects of both the explicit as well as the implicit arguments. So in this paper that you're reading, you're actually going to be reading about the Valgrind tool. If you're not familiar with the Valgrind tool, I suggest that you actually go and Google it. Valgrind is a tool that is very popular for debugging. It's a much more advanced version of GDB, if you will, right? It can do much more than debugging. But Valgrind is a very popular debugger. It lets you instrument the program at runtime and do lots of things to understand how the program executes. So Valgrind is a very popular tool and it has an intermediate language called Vex. Just like that, there is a project called BitBlaze that analyzes x86. Again, all of these are terms that you can go and Google. The BitBlaze project really developed a number of pioneering techniques for x86 analysis. And it uses an intermediate language called Wine. And in fact, the paper that is assigned for reading for this particular lecture by James Newsom and Don Song, that paper was one of the early papers of the BitBlaze project. That project, as well as its subsequent that paper, as well as its subsequent follow-ups, resulted in the creation of the BitBlaze project. Okay, so you won't read anything about the Wine intermediate language in that paper. This is something that evolved over the next 2-3 years after that paper was written. But in any case, right, I mean, you can actually go and download the code of BitBlaze. It has an intermediate representation for the x86 instruction set. So the nice thing about intermediate representations is that it's much easier to parse and identify the operands. Again, to draw a relationship between this lecture as well as a prior lecture, you have seen intermediate representations before. The intermediate representations that you saw before were in the case of the soft-bound lecture, where the soft-bound transformation was applied at the level of LLVM intermediate representation or LLVMIR rather than at the source code or at the x86 level. The reason there was because the LLVMIR had type information and it was a much smaller set of instructions in the intermediate representation to work with rather than the entire complexity of the x86 instruction set. Essentially the same thing here. Okay, so for example, this reel, which is a part of this tool from Zynamics Binnavi, I'm not too familiar with it. According to this presentation, according to the author of this presentation, uses only 17 instructions in the instruction set. Okay, that's pretty good. You just have to think about 17 instructions and writing your taint propagation rules for these 17 instructions. Okay, so you can see over here, there are some instructions: subtract, and there's an and there is probably this is a string operation. I'm not entirely sure. All right, so now let us look at taint objects, how objects get initialized with taint and various instructions. Okay, so taint objects, we have to understand, are the granularity at which you decide to store taint. So if you think about the granularity at which to store taint at the C programming or the C++ or the Java programming level of abstraction, what you generally think about are things like variables, because those are the objects that you, the programmer, see and that you directly manipulate. Now you can obviously, you can store one bit of information with every variable, uh, every integer variable. For example, four bytes of an integer, you can store one bit to determine whether that integer is tainted or not. And so if you do that, then your objects at which you're doing taint are programming level variables. But for this lecture, because we are dealing with the x86 architecture, we are going to look at Taint objects at a much lower level of granularity. In particular, our Taint objects in this case, when we are looking at x86, are going to be memory locations and processor registers. So the advantage of doing taint analysis at such a low granularity, which is memory locations and processor registers, is that it allows you to do extremely low level taint tracking. You can track taint at the level of individual memory locations, so you can determine whether a particular byte in memory is being tainted by the untrusted attacker provided input or not. Okay, so you, for memory objects, you can even keep track of the initial memory address, and you can keep track of the area size. You can group together, for example, the taint. So if you want to, let's say, say that an entire integer object is tainted, you don't have to store one bit per byte. You can just say that, I'm going to group together these 4 bytes and then store only one bit. That's perfectly fine even at this level of granularity. And even objects, right? Register objects. You can keep track of the register identifier and keep a bit level track for each register. So that is how you track taint at the level of objects. Okay. So the tainted objects, you have some representation to store the taint. For the register as well as memory, you store at some level of granularity this one bit that determines whether the object is tainted. Okay, so taint check, for example, in Valgrind, it uses byte level taint tracking. So every byte you associate a bit, determine whether that byte is tainted or not. Okay. It need not be always at this level. As I said, you can group together a bunch of memory bytes, can group together a bunch of memory locations and just have one taint bit for it all. That's perfectly fine as well. So on the left hand side of the slide, for example, you see the register. You're storing the taint values for this register. The register AL, for example, is the least significant bit of the register EAX, and you can store taint at that level, or you can store a taint value for the entire register. That's also fine. Okay, and over here you're storing taint for a particular tainted area where you store the beginning address as well as the size. Then you say that if that taint bit is set, the whole thing is tainted. That's one way of doing it. You can also store one bit of taint per byte in the memory object. Of course, the more metadata, so this taint information is also metadata. The more metadata you have, the slower your execution of the program is going to be, because now your runtime has to do much more work to propagate taint. Okay, so the instruction set architecture, it can be divided into several categories, right? You can think about assignment instructions that take information from some source location and then store it to some destination location. You can think about Boolean instructions that are operands that combine two arguments and provide a result. You can think about arithmetic instructions. You can also think about about string instructions. So for example, repeat move SB or repeat scas B. These are all string instructions. Again, these are all part of the x86 instruction set, right? I mean, this is not something that you would see in a typical reduced instruction set architecture, at least as part of the ISA. But x86 is much more complex. Even though it internally uses a reduced instruction set architecture, the instruction set itself is rather complex. So you will see string instructions and so on. And also branch instructions that transfer control flow. Things like call, return, jump, unconditional jump, conditional jump, and so on, right? So these are the various ways in which you can categorize the instructions. For each set of instructions, we have to come up with a set of taint flow rules. So let's start looking at assignment instructions. So here we have move EAX dword pointer in this location, which is basically saying, take the stuff that is stored in this memory location and store it into this register EAX, right? You're copying stuff from memory and storing it within the register. So the move instruction this particular case is copying the taint information of the source. If it is tainted, even the register gets tainted. Okay, so the taint goes from here to here. This was not tainted, EAX would also not be tainted. We can now think about, I'm going to show you how you propagate taint through Boolean operators. You can extrapolate to the other Boolean operators not shown here. And the rules are also going to be similar for various arithmetic instructions. Okay, so let's look at the most common Boolean operators and or and XOR, and then see how taint propagation happens. Okay, so the main goal of the analysis is to see if the output should be tainted based upon the values of the inputs. If the inputs are tainted, then the output also gets tainted. And you should also take special care in case both inputs, in case of both inputs to be the same tainted object. Okay, so let's take the AND truth table, right? So if A is tainted, right? Um, then essentially what happens is that if A and B are both 0, then the result is untainted because the result here does not depend upon the value of A. So here I'm actually talking about the values of two Boolean variables. I'm not talking about the taint values. I'm actually talking about the actual values of two Booleans. If A is 0 and B is 0 and A is tainted, okay, and B is not tainted, then A and B is also not tainted because the value of the result A and B is determined by B, right? So even if A was tainted, it does not matter because the end result is going to be determined by this untainted object. So you can as well remove the taint from this location over here. Uh, and so even if A is tainted and B is not tainted, the result here need not be tainted. Okay. If you were to, for example, say that A and B is also tainted because you use this A, because and A was tainted, you will end up tainting way too many objects. So this is a way to control the flow of taint also. Okay. All right, and if A and B is equal to 1, then the result is tainted because A controls the result of the operation. So if B is not tainted but A is tainted and both are 1, A and B is tainted, okay? And the result is because, and the reason is because if A is 0, the result here would have been 0, and if A is 1, the result here is 1, okay? So the output, the value of the output crucially depends upon the value of A, and therefore you have to say that the output is tainted if the input is tainted. Okay, whereas in the first case where both values were 0, if B, the untainted variable, is already 0, whatever A is, the value is always going to be 0, so you can remove the taint. Okay, so that's how you propagate taint. Let's look at these two. Right, in this particular case, if the value is 1, of course over here it's going to be tainted because the value of this 0 over here was the one that determined the taint over here. Okay, now in this particular case, what is it? If A is 1 and B is 0, the output is 0, right? um, and the output is going to be 0 anyway because of B, and so you can say A and B is untainted. Okay, um, so if the value of A can actively control the value of the output, then you say that it's tainted. Okay, that's how you combine taint. So here's the OR truth table. Okay, and if A is tainted over here and A and B are both equal to 1, then the result is untainted because the value would have been 1 anyway, right? Just the dual of AND. And if A and B are equal to 0, then the result is tainted because A can control the result of the operation. So basically, if some of the if the input, if the value of the input to an operator such as AND or any other operator, if the value of the input can determine the value of the output, you say that the taint of the input gets copied over to the taint of the output. Taint value of the taint tag of the input gets copied over to the taint tag of the output. Okay, just like that over here, if you've got XOR, if A is tainted, then all possible results are tainted independently of the value of B, um, except in the special case of A XOR A, of course, where the output is always going to be untainted because the value is always going to be 0. So even if A is tainted, it does not matter, uh, because the output is always going to be this constant value 0, and it's not something that the attacker can control, right? Because always 0. The only point is if the output can be can be controlled. So if A is tainted, then all possible results are also tainted, independent of any value of B. Because XOR is a symmetric Boolean operator, same rule applies even if you're considering B instead of A. Okay, so for the tautology or the contradiction truth tables, the result is always untainted because none of the inputs can influence the result. Okay, so tautology means the truth value of the output is always true. Contradiction means the truth value of the output is always false. Okay, so you if you have an operation that always produces a constant output, then this is a good way of saying that you do not have to taint the output. Okay, so if the output is always going to be a constant, or the output is a constant, uh, once you fix the value of one variable, you can untaint that because that constant is anyway going to be that same value irrespective of what input the attacker provides. Okay, so constants are generally untainted. This also applies to literal values that are there as part of the program's execution because because the value of the literal cannot be changed. Okay. Okay, so over here you've got AND AL, which is the least significant bits of the EX register together with a constant value. So the constant value is 0xDF, it's 1 byte. As I said, a constant value is always untainted. And let's say that the register, the lower bits over here are tainted. If you use the AND operator, then the result is being stored in AL. And so the result here is also going to be tainted. Okay, so that's what that is. And DF is nothing but this particular bit value. So AL is the least significant byte of the 4-byte register EAX. Okay. The only special case over here, as I was already mentioning, is XOR AL. And if AL is still tainted, if you're doing an AND, because the result is always going to be 0. If you XOR a value with itself, the output is always 0. You can remove the taint. Okay. It's always a constant because the output is always a constant. You can remove the taint tag and you can call that register value untainted. Okay. So this is how you can remove taint or prevent the blow up of taint as the program executes. Because if you were to keep AL tainted, your analysis is going to be conservative, right? You're saying it's tainted because value is potentially coming from an untrusted source, but it's too conservative, right? You can say it's untainted because the value of AL is not, it's always a constant, it's 0. Okay, so you have to do similar reasoning about arithmetic instructions, add, sub, divide, and so on. And arithmetic instructions can, if you think about how arithmetic instructions are implemented at the machine level, they are all implemented using Boolean operators, right? So add can be expressed using only AND and XOR, right? If uh, uh, and so that is one way to think about your taint propagation for arithmetic instructions. But generally speaking, for arithmetic instructions, if we generally say that if one of the operands of the arithmetic operation is tainted, the result is also tainted. Okay, so the key thing about arithmetic instructions is to remember that it is not just the output register or the output memory location that is affected, but also an implicit register called E flags, which is affected um, by the arithmetic operations. So E flags is the x86 register that stores various things, such as the carry flag, right? If you're, for example, doing multiplication or you're adding two bits, 1 and 1, the carry bit tells you whether you have to carry over anything when you're adding to the next digit. Okay, so the E flag stores a bunch of these registers of these flags that are often set by the arithmetic operations, and so care has to be taken whenever you're talking about these arithmetic operations to determine whether the E flags register is also tainted as a result of performing this operation. All right, so string instructions in x86, you can think about strings as just a linear array of characters. So x86 string instructions, there are quite a few, and it's actually, as I said, it's a complex instruction set architecture. So again, the general rule of thumb over here is that any string instruction applied to a tainted string will also result in a tainted object. If you don't want to do a deep analysis of every such of every such string instruction, you can take, for example, this thumb rule that if your input to the string instruction is a tainted string, the output is also a tainted value. Okay, so if you want to, for example, calculate the string size of a tainted string, the integer that results, that depicts the string size, is also a tainted value. Or you want to look for some specific character and set a flag if it is found or not found. You got a long string and you're doing a search for a particular character, then the boolean value of whether that character is there in the string or not is also supposed to be tainted, right? So that's the idea over there. All right. Let me just. So let us try to understand the lifetime of a tainted object. The A tainted object comes to life when you make an assignment from an untrusted object. So, for example, if you're moving a value from an untrusted user buffer, for example, pointed to by this register ECX, and the contents from that buffer get into EAX, and so that's how you create taint into EAX. Um, so now if you do an assignment from a tainted object into another one, taint propagates, and that's how you sort of create taint. Now, taint goes away or taint is removed from an object. So, for example, if your registered EAX was already tainted, but if you're now going to copy this constant value 03 hex, sorry, 30 hex into EAX, the taint goes away in EAX. So, EAX, even if it was previously tainted, will now become untainted because you're copying this constant literal value. And as we spoke about in the previous slides, the constant values are um, are untainted, and so you copy it into EAX. And again, if you have any output that's always a constant, you can also remove taint. For example, XOR EAX EAX is one way to remove taint. Okay, so let's look at slightly more advanced forms of tainting. Um, so the level of detail is one of the ways in which, oh sorry, the granularity at which you taint is one of the things at which you can do advanced tainting. So you don't have to taint every memory object. You can also, taint an entire group of memory locations and call that taint. That you can associate one bit of taint together with that. So, for example, there's a tool called Taint Box, which is built on top of this box framework, and it does not taint comparison flags. Okay, so whereas others, for example, taint assert as well as a paper that you're reading, it taints at the byte level. Okay, all right. So we'll look at some aggressive taint methods, right? So we are now going to talk about a form of taint called implicit taint. So let's look at that. So uh, you can also do bit level tracking instead of byte level tracking, right? So conditional branch instructions that, for example, take the EIP register, all the flags affected by the E flags register, you can monitor at the bit level. So E flags is a register, 4-byte register. You can track taint at every bit level of this E flags. Okay, so you can also taint code at execution time, and you can taint at the control flow block level of the control flow graph, right? You can say, look, I'm going to now execute this piece of code, and because it's the piece of code that I'm executing over here was determined by a flag that determined that you should take the true or the false conditional, and because the conditional variable was tainted, this block of code is also tainted. Okay, so if you've got two branches of an if then else, a true branch and the false branch, and the conditional to the if itself is tainted, then the entire block of code that you execute, be it the true branch or the false branch, that entire thing gets tainted. Okay, so that these are all various advanced methods of tainting, and we'll look at them. Okay, so let's look at the comparison instruction, right? I mean, over here, we've got x86 instruction over here that is basically going to check whether you're comparing the value of EAX to 20 hex. And the pseudocode is just like this, right? You're going to do temp equal to EAX minus 20 hex, and then you're checking whether it's equal, and you're also going to set some flags based upon the value of temp. Okay, so you want to check whether there's an overflow or whether you have to do a carry when you're doing this. So 0 bit basically tells you whether the value is 0. You also have parity bits and so on. So you might want to track Taint at that level. Okay. So the comparison instruction will affect each one of these flags. And so you have to propagate Taint in that particular way. So conditional branch instructions, let's look at this particular case. You're comparing EX against 20 and you're saying, look, if it's non-zero, right? In other words, I'm comparing EX against 20. If EX is equal to 20 hex, then actually go and jump on to a particular hexadecimal location. Okay, so um, if the value of the register is, if the value, if it so turns out that EAX is equal to 20, then this is the branch target. Otherwise this will be the branch target. So this is in some sense like how you implement a true as well as false false if then else statement. Okay, so if this executes if this is true, and sorry, if this executes if it is 0, and this executes if it is not 0, you start from executing over here. So you've got a code block that starts over here, and the entire code block goes till here. This one over here would be the false block. Okay, likewise at the end of the true block you'll have a goto that ends up transferring control to the merge point of the if then else. Okay, so taint comparison flags like the 0 flag we already tainted, but branch instructions also affect the EIP register, the EIP instruction pointer. The reason the branch instruction affects the EIP register is because based upon the value of this conditional over here, you change the value of the instruction pointer either to in this particular case 010DH, which is the instruction just following the JNZ, which is the target if it's 0, or else you go over here, right? So the value of EIP depends uh, very much so on the value of EIP depends, the taint value of EIP depends very much upon what the value that is being compared. Okay, so okay, so you come. So essentially, the if the jump is dependent on the value of a flag, then you also taint the value of the instruction pointer. Okay. All right. So the question then is, how do you express in the intermediate language the conditional jump, and that shows the relationship between the 0 flag and the EIP or the instruction pointer. Okay. So one way to do it is to actually think about the delta between the EIPs, that is the distance in terms of how many bytes there are between the instruction just following the JNZ and the instruction that is the start of the of the uh, of the other branch of the, so from 08CH all the way to the instruction just before this exchange is what happens if you were to just fall through after this jump, and jump non-zero would be to this 100, so this would be this, and the delta is the distance between these two instructions, right? So if you had this particular notation to treat the true as well as the false blocks, then you can use the following formula for conditional jumps. So NIA is the next instruction address after the conditional jump. TT is the true target, which is the address of the target if the comparison evaluated to true. And in this particular case, that would be the very next instruction, and FT is the false target. Sorry, true is it would be 100, and the false target is 8CH, the very next instruction. And B is the flag value, which is always a Boolean, and D is the delta, right, which is jump instruction, which is the true target minus the false target, the absolute value. Okay. So now you can express the EIP is equal to the next instruction address plus B times D. Okay, that's the way um, that you would express the EIP. Okay, and so if you were to express it this way, then you can just carry over the taint tags from these things. Okay, so the delta in this particular case is absolute value of 100 hex minus 88 hex, okay, which is 13, and the next instruction address is 100. Therefore, EIP is equal to 8CH plus Z, the zero flag times 13H. Okay, so whether this is zero or not, that determines what the value of EIP will be. And this way of doing it also allows you to propagate taint tags. So if you have a tainted instruction pointer, what is the consequence? So the consequence of having a tainted instruction pointer is that the entire target code block of the control flow graph is tainted. Okay, if your control flow block, the entire code block is tainted, then every variable that is the target of any assignment inside that code block is also automatically going to be tainted. Okay, so prototypical way to think about this is the following, right? Consider a program of the following sort. Let me just go and open up a Word window and then show you um, the following program. If x equal to 0, do the true branch, and uh, else do the false branch. Okay, uh, and let's say that the uh, value of x is supposed to be sensitive. Okay, then based upon, so just let's look at this true branch, and let's just say that the true branch sets the value of some y equal to 1, and let's say the false branch sets the value of y equal to 2. Okay, and you have a statement over here that, let's say, prints the value of y. Okay, uh, so in this particular case, if x was tainted and it was a variable that was tainted, note over here that you have a program pattern where, even though the value of x is never directly copied into the value of y, the value of x is determining the value of y by means of the if then else statement. If you were to do taint propagation for the y equal to 1 statement or the y equal to 2 statement, you would find that y is untainted in both cases because you're copying from a constant value, right? As I said, constant values have no taint. Therefore, if you were to just consider the simple taint analysis, y equal to 1 or y equal to 2, y would be untainted. The only way, and in this particular case, the value of y is clearly being affected by the tainted value. X is, for example, something that is controlled by the attacker, okay, um, or input by the attacker. So in this case, you can clearly see that based upon the value of y, you can determine what the value of x was, or at least whether it was 0 or non-zero. And so the value of x determines the value of y. Okay, so there is an implicit or indirect information flow control in this particular case. And by following this particular method, where your EIP is tainted. So if your EIP is tainted, when is your EIP tainted? Well, if you look at x, because x is tainted, the conditional operation over here, which would be a conditional jump, the corresponding conditional jump is also going to be tainted. Therefore, the entire code block that executes either in the true branch or the false branch is going to be tainted as a result. And as I said, any variables that are assigned to within the true branch or the false branch also get tainted. Therefore, y will get tainted because the code block that corresponds to the y equal to 1 instruction or the y equal to 2 instruction would also be tainted. As a result, we can now transfer the taint of x to y through the control flow graph, through the nodes of the control flow graph. Okay. Um, you can also use taint analysis to solve reachability problems. Okay, so if you've got, let's say, a sound recording function called play sound, and you want to create a particular mp3 file which will allow you to execute a particular code block um, within that function in play sound, then all you have to do is to run the mp3 file through a taint analysis tool and see whether that particular taint input is going to taint block number 357 in play sound. Okay, so you can solve these reachability problems using taint analysis. Okay. Last slide, tainted instruction pointer is a sufficient condition, is not a sufficient condition to determine vulnerability. Okay, so you can potentially have false positives there. So the contents of the memory location pointed to by EIP must also be tainted. Okay, so if the if it is vulnerable, if is vulnerable is true, then both the instruction pointer must be tainted as well as any values that are being dereferenced or assigned to by that location must also be tainted. Okay, just like in this particular program that I showed over here, y gets the taint and the taint is propagated from x to y. All right, so that's it about taint analysis. The paper which you have to read also contains a very interesting application of taint analysis to the problem of what is called signature generation. So signature generation talks about how to generate the signature for a particular attack. So let us quickly go and look at that. So over here, if you go and look at the section of, so by the way, the paper talks about various ways in which to run your taint checker to detect various kinds of attacks, including format string attacks, buffer overflows, double freeze, heap overflows, and so on. And they talk about various things that are considered as taint sinks. So do you taint a return address? Do you taint the jump address, function pointer, system call arguments, the function call arguments? All of these things are taint analysis. So format string, for example, one way to do a simple format string taint analysis is to check whether the argument to the to a printf function can potentially be controlled by the attacker. Okay. All right. So the paper contains a performance evaluation as well as a robustness evaluation of whether it's able to detect any real attacks. And this particular portion on section on automatic signature generation talks about how you can determine a unique signature or a pattern that represents an attack. Okay, so it's actually fairly straightforward. They also give you some examples of signatures in the paper. So I would ask you to go and do self-reading of section 6 of the paper. I've covered most of the other concepts that are related to this paper. All right. So enjoy the class. I hope you enjoyed the class. If you have any questions on taint analysis, please feel free to post in the Teams group and I will try my best to answer as soon as I can. All right. Thank you very much for your time.